I'm looking at this idea of intervals of what? Concavity. So today we're going to talk about these things. Looks like we got some more people. How you doing, Blanca? How you doing, Adrian? Good morning to you guys. We got more people on this spooky Halloween day. Okay, so take a look at what you guys see there. We're going to talk about this idea about concavity, okay? And I'm going to lecture today with our Halloween colors. Okay, so I hope you guys don't get scared today. Nobody's dressing up. Nobody dressed up this weekend. Oh, good for you guys. Okay, let's talk about concavity. So I'm going to bring in a graph, maybe, or a picture. Okay, so I'm going to draw a picture for you guys here. And let me do a little better picture. I know it's going to be something that's a bit simplified, okay? Here's point P. Okay, point P. So if I were to say to you guys, remember what we talked about? What did we talk about last time? Do you guys remember? You talked about this thing. Hopefully you guys can recognize this. This is at A, maybe, and so the point here is A, or we can call that C, because there's a critical value probably, right? And this will be efficacy, right? So at this point, C, comma, efficacy. So I have that point. And so there you go. So if I said to you guys here last time, just by this picture, you know, this, you're walking left to right and you get over here. What are you doing in this portion of the graph? Do you guys remember? What are you doing? This portion. It's odd. Doesn't want to highlight that as like I think. Oh, it's weird. Let's see if it does a different color. Oh, I don't know. Because of the black background, it's not working as well. So, okay. So let me do this then. If highlighters aren't working. You see this here in gray. What do you guys know about that interval from negative infinity up to C? What is your function doing? You're walking uphill. What does being uphill mean? F is what? Increasing. Okay, you guys okay with that? So what does that mean to be increasing? Your first derivative is what? Positive. So far, so good? And then what about over here? What are you doing now after C? And you're going now, walking in the other direction, or you continue the walk from left to right. What do you guys notice about that in gold? F is what? And what interval? Yeah, let's kind of, that's from C now to infinity. F is decreasing, right? Okay, and that first derivative will be what again? Negative. Is that true? So I just want to point this out with this picture. Oh, it doesn't like to highlight. Okay. What happens if I take the picture out? Oh, no, the picture will move. Yeah. All right. You learn something every day. And, of course, you guys know at P you have a horizontal tangent. Altangent. And that derivative equals 0. Horizontal tangent, okay? All right, now, I want you guys to know one thing here. For that kind of picture here, okay, your first derivative changes. Okay? F prime x changes. Is that right? It goes from what? For every point on that curve, you have a tangent line. And I want you guys to notice something about that tangent line. You may get 0 again, but what's the story here? As you go left to right, what do you guys notice about the tangent line? Okay. Remember we said we always work left to right? I want you guys to know. M tangent is doing what? You're going from positive slopes to negative slopes. Is that true? So I'm going to say M tangent is decreasing. This is an important detail. The slope of the tangent line is what? Decreasing. Okay? Now, what does that really mean? Okay? That means your derivative is what? Negative. Remember what it meant to be decreasing? Right? You're not talking about this, you're not talking about whether the function itself is increasing or decreasing. You're referring to the slope of the tangent line here. This thing. Okay? Let me take that back. Yeah. Is negative here. Oops, nope, sorry. Take it back. The second derivative is what? Negative. Okay? So I want you guys to understand this great detail. That I'm saying this. F prime evaluated at that point x is decreasing. So that means the second derivative is what? Negative. This is kind of the notation behind it. Okay? F prime, well, derivative of f prime here is less than 0. And that's known as the second derivative being less than 0. So what you're looking for, ladies and gentlemen, is a second derivative being negative. Okay? This is what we call being concave down. You're concave down. The second derivative is what? Is negative. Okay? Now think of concave down this way. That if it were to rain on this, this does not hold water. This is what we say. Does not hold water. This is what we mean by being concave down. Doesn't hold water. Okay, it's like a cup that's upside down. All the water's coming out. Doesn't hold water. You guys agree with that? That's a picture of being concave down. Compare that to the following here. Every point here, what's happening with that M tangent here? Okay, this is a situation where we say holds water, by the way. Okay, you hold water here. So let's take a look at this M tangent. You got these tangent lines. Here's M tangent, okay? M tangent is doing what? right? The slopes of those tangent lines, what do you guys know? You're going from decreasing to 0 to positive. So M tangent here is increasing as you go how? Left to what? To right. So you say, what is M tangent? Well, M tangent is a derivative, is that right? So what happens here is the derivative of that first derivative, because it's represented by what? M tangent. There's your M tangent. In order for that to be increasing, that derivative is what? Positive. And so what you really have is a criteria here that the second derivative being positive is when you have concave, what we call concave up. So this is really the idea here. And being concave up is where your curve holds what? Where the curve holds water. Concave up, concave down. It's the first derivative increasing, which means you have the double derivative there being positive. Okay, because that's M tangent. Similarly, being concave down, remember this is M tangent right here. Just to illustrate again, that derivative will be negative. That's the second derivative, and it's negative. It does not hold water. Does not hold water, holds water. So at the end of the day, what are they going to ask you? They're going to ask you these kind of questions, ladies and gentlemen. Should we go back to our spooky colors? They're going to say, determine the interval of concavity. Or determine where your curve is concave up or concave down. When they mean by where, interval. Okay, you guys okay with that? So let's do a first example here. So if you look at this, in honor of Halloween, what's our first example here on this sheet? You say, boy, Mr. Judge, you have those same exact questions. What are they? 5 minus what? 3x squared, is that plus what? X cubed, good, because I can't see, old man Judge, right? He can't see. All right. So we actually went through a bunch of these questions already with what? Finding the intervals of increasing, decreasing, and you go, you're going to give me the same function? I'm going to say, yes, but what are you looking for now? Where does a curve hold water? That's called concave up. And where does the curve what? Do not hold water, concave down. I don't know. What do you guys think? Should we adopt the... Does that scare you guys there? Can you see that? Is that... The color's kind of scary. I can't see. Is that clearer to see than the white? I don't know. Maybe. Is that... All right. Let's find the second derivative. In other words, when they ask concavity, you know what this is code for? Sign analysis on what? The second derivative. There you go, ladies and gentlemen. Sign analysis on the second derivative. That's all you got to do. Sign analysis on the second derivative. So, okay, hopefully you guys did some derivative question homework. So here you go. You guys ready for that? So what's the derivative of a constant? Isn't that 0? This is what? 2x. And then what's this? 3x squared. Is that true? So, okay. My first derivative will be negative 6x plus 3x squared. But what do I need? I need the second derivative. Is that true? So say, what's the second derivative? You guys know how to get a second derivative? Take the derivative of the what? First derivative. Do it again. Okay, here we go. This derivative is 1. What's this? 2x. What do you guys end up with? This is going to be what? F double prime is negative 6 plus what? 6x. Okay, good. So like on a test, what do you think they're going to ask you for? And say, hey, what's that second derivative? But notice, don't you have to get the first derivative though? So in order to get a second derivative, you got no choice. You're going to get a first derivative. They're really going to ask you both questions. They're going to say, where is the function increasing, decreasing, and what are the intervals of concavity? They're going to actually ask you both. So in other words, you do sign analysis on both. Remember the particle? Remember I gave you in the last test, the particle increasing speed and decreasing speed, where it's speeding up. Remember speeding up and slowing down? Same, similar kind of thing. You got to do sign analysis on both derivatives. So I hope you guys did some sign analysis because I've been talking. I'm not. Yeah, sign analysis. I gave you guys that video on that, right? All right, here we go. What do we do? You guys ready? Here's what you do. Notice, isn't this a linear function? Okay, so linear functions, you just simply set this equal to what? 0. Okay, and so translate, do some algebra. You get negative 6 equals negative 6x. Divide both sides by negative 6. And what do you get for x? X equals what? 1. Okay, you guys okay with that? All right, okay. Now what do you guys do? This is sign analysis. Is that true? So what about your function? What was the domain of that original function? Right? What is this? Right? You know the domain here is what? All real numbers. Why is that an important detail to know? Okay, because when you do your sign analysis now, what do you have to have? You got to have what? Like the whole real number line. Okay. So at 1, what do you guys know? You have the second derivative. This is the second derivative now. That second derivative is 0. Okay, you guys okay with that? Oops, positive 1, not negative 1. Okay. Now the digit to the left, or not a digit. Yeah, give me a number to the left. What's to the left of 1? 0. What's to the right of 1? 2. What do we call these here? Test points. What's that function here? Okay, so when I plug in, what number do I plug in? 0. Isn't that a great test point? Right? What do you guys notice? Isn't it -6? Right? So what do we know? Region 1 is negative. Okay, you guys okay with that? What does that mean? Concave what? Down. Second derivative is negative. Is that true? All right, now what about the next test point? You go, okay, let's plug in now too. I know, 6 times 2 is 12. 12 minus 6, what do we know about that? That's going to be what? We call this concave what? Up. So there you go. You have what? Concave down, concave up, ladies and gentlemen. Spooky, spooky, spooky. So how do you answer this question? Do you guys know? This is how you answer. F is concave down on the interval from -infinity up to +1. F is concave up on the interval 1 to infinity. So if I go back, I think we colored this green. Concave up is green. Okay. Concave up. That's the interval, 1 to infinity. Concave down is what? Is this way. And there you go, ladies and gentlemen. That's your sign analysis on the second derivative. This is the meaning. Let's look at the curve here, right? What's the curve? 5 minus 3x squared plus x cubed. So this is my curve here. I'm going to go to, where am I going to go? Where are you, Desmos? Where are you hiding? There we go. We still have that. And I can touch some points. I can't touch every point. So I might just put the point here, 1. When x is 1, what is y? 3, it looks like. So I'm going to say 1, 3. Orange in honor of Halloween, okay? You guys see that there? So notice this. The interval to the left when x is 1, does that hold water? Say what? No, it doesn't hold any water. You guys agree with that? What about the interval to the right of 1? Does that hold water? Sure does. Easy breezy, lemon squeezy. So, you might say, what about at 1? Well, at 1, I'm going to give you guys another definition here. Okay? This is a special thing. Definition. The point on a curve where concavity changes from up to down or down to up is called an inflection point. Okay? This is the definition of what we call an inflection point. It's where you change concavity, but notice you must be on the what? On the curve. Okay, so you got to be on that curve. And you go, well, what does that mean? Right in here, ladies and gentlemen. This is what we're talking about. You went from concave down to concave up. At what value of x? When x is 1. So this has a inflection point when x is 1 and the curve is f of 1. Okay, it has to be on the curve, right? To make sense. So you say, oh, how do I find the y coordinate? Well, go back and plug in. Plug in when x is 1. Okay? You will get 5 minus 3 plus 1. Is that right? And that's 6 minus 3, that's 3. So plug in the value. Sure enough, you're going to get what? The y coordinate. So this is what they expect, the x and y coordinate value. This is where you have an inflection point on your curve. So the curve has an inflection point at 1, 3. Okay? And it has to be on the curve. So anyway, does that make sense? It's a very special point. That's when you change concavity, up to down or down to up. So you say, how do I know? Because you go back to your sign analysis and take a look. Do you go from negative to positive anywhere? Yes, we do. Do you go from positive to negative anywhere? No, but if you change from negative to positive, then you have a special situation. Okay, what do you guys think? Is that okay? Easy breezy, lemon squeezy? It's not too bad. So hopefully you guys did some work on sign analysis and did some work on derivatives. If you did, you're on your way, ladies and gentlemen. Not that big a deal. Okay? All right, let's look at some more examples. I'm just looking at this sheet here. Okay, we got the fraction example. Good. X over x squared plus 4. Does anybody remember on their notes what that first derivative was? Because I'll go back and take a look on mine. Is it in your notes? You guys have that? You say notes on what day? Increasing, decreasing. Not that one. Let's go back. I think it was number 2. Was it x squared over x squared plus 1? Is that the one? Yeah. Okay. Is this the derivative? Oh, it's x squared on that one. Okay. Oh, maybe I did a typo. Maybe it's me. Oh, I guess we have to do it maybe then. Oh, it is x squared. Typo. Okay, it was x squared. Good. So go back. What was that derivative? You go, oh my God, Mr. Judge, they're going to make me do that? Looks like. Wow. Okay, let's go back. Ah, what am I doing? X squared plus 3. This was the derivative we got. And I think I think we erased it, right? Or we moved it. It was 6x. Yeah. Okay, I'm going to copy this one. There we go. So we said, Mr. Judge, where did that one go? I'll say, take a look at your notes in the video. We did this already. Okay. We need to do what now? The second derivative, right? And that's the derivative of what? The first derivative. So you'll have x squared plus 3 squared. And this is what? 6x. All right. And what am I doing? I'm going to go back to my spooky colors. Halloween only comes around once a year. I'm surprised you guys didn't dress up. Maybe later today? Yeah, this year, I hate to say it, I was a scarecrow. You know, it's funny. My wife says, "You know what you're going to be next year?" I said, "What? Isn't that funny? I'm told what I'm going to be." Go, what am I going to be? She goes, "A good idea that you come as Frankenstein." And I'm like, "What? What? Frankenstein? Could you imagine?" You know why she said I should be Frankenstein? She says, "Because you have a square head." I said, "Oh, really? Don't go there. Oh." So our daughter, Melinda, has a square head too because we have the same head. Square head. And isn't that horrible? Is that mean? What do you guys think? If somebody said that to you, what would you think? I just want to know. Should I get mad? Square head. Jesus. Let's look in the mirror. How many of us have a square head? How many of us have an oval head? Anyway, whatever. So I guess I'll have to paint my skin green or something. I have no idea what the plan will be. I got to look it up. How do you come as Frankenstein? It's actually a pretty good costume. All right. So yes, I'm going to be celebrating tonight, scaring kids. But scarecrows aren't scary. Yeah, and I want to be a friendly kind of costume. You know, I don't want to be a creepy costume. I don't think that's like kind of weird to me. I don't know how you guys feel. Like one year, all these kids were those like, what were they, scary clowns or something? One year, everybody was these scary clowns, and I was like, everybody showing up to your door, you know. Anyway, all right, what's the derivative of x? Isn't that 1? What's the derivative of x squared? Isn't that 2x? So here we go. So x squared plus 4. Now that's times 1, okay? Minus x times 2x over the x squared plus 4 squared. So x squared plus 4 minus 2x squared over x squared plus 4 squared. So what do you guys get now? What do you guys think? What is this? Isn't that just, oh, it's 4 minus x squared, I think. You have x squared plus 4 parentheses squared, and that's the second derivative. Easy breezy, lemon squeezy. Now, remember, when you do sign analysis, you got to be concerned with two things. Is that right? Because this is a fraction. So remember, when you do your sign analysis, you have a numerator over a denominator, right? So this is the sign analysis portion now. Sign analysis on the second derivative. So you set that numerator equal to 0 here. You get what? 4 minus x squared is 0, which means x squared is 4. Is that right? And that means x will be plus or minus square root of 4, or x is plus or minus 2. Okay, so I'm going to use that. I'm going to keep a different color, though. What about the denominator? What do you guys notice about this here? Right, what do you guys remember about that denominator? X squared plus 4 squared, right? What is this? Is that equal 0? What do we say? Never happens. Is that right? What I'm saying is your denominator is never equal to 0. At least not for a real number. Okay, now you might say, well, how do I know? Well, this means x plus 4 is plus or minus square root of 0. And that's x squared, yeah. Which means x squared plus 4 really equals 0. So it means x squared is negative 4. We're not talking about complex numbers. So again, the denominator, what? We say this never happens. So this does not contribute to sign analysis. Okay? We only have the values negative 2 and positive 2. The denominator just isn't ever going to be 0. Because if you try to solve that, it's impossible. You get imaginary solutions. So we're not looking for imaginary solutions. We're looking for real number solutions. So you say, okay, what does that mean? Well, negative 2 and positive 2. So when we do our sign analysis, I'm looking for that second derivative. It's right here. Okay, what are your test points? What do you guys think? What do you use as test points? Maybe what? Negative 3. What else? 0. Positive 3. These are all test points. Okay, we're going to test each region. How do you test a region? Just plug in the test points. If I plug in negative 3 here, right? What do I get? I get 4. Let me change colors. 4 minus negative 3 squared over negative 3 squared plus 4, everything squared. You guys want to know something on the denominator? That's always positive, right? So I don't even care about that one. I only care about the numerator. So then I get 4 minus 9. You guys know what 4 minus 9 is? This is going to be what? Negative. So I get negative here. Now this is on the second derivative, not the first derivative. So I draw this picture. Right, what is this picture of? Does not hold water. Concave down in region 1. Okay. So I'm just interested in not even the values. I'm interested in the sign. Do the same thing for region 2. You say, what represents region 2? The 0. So the denominator is positive again. We don't care. But what's 4 minus 0 now? What's the numerator going to be? It's positive. Concave up. All right, you guys okay with that? Easy breezy lemon squeezy. Now plug in a 3. Right, again, you're going to have 4 minus 9 over here. Is that right? And that's going to be negative. The denominator is always positive. So, okay. Negative now. Oops, sorry. Concave down. Okay, so let's draw our conclusions now here. I'm going to erase this. Erase this one. What's the conclusions here? What are we going to say? F is concave down. I forgot what color we were using for concave down. I don't remember. Concave down is pink, I think, and concave up is green. So, okay, pink. Can you guys tell me? Here, where else? Where's concave down? Yeah. Union what? Right, isn't that concave what again? It's concave down on these intervals. F is concave up where? -2 to 2, right in here. Okay. Do we have any inflection points? Are there points where you change concavity from negative to positive or positive to negative? Inflection points? Here and where? Here. Oh, what am I doing? Yeah, concave up. -2 to positive. Oh, here we go. Sorry. There we go. What do you guys think? Pretty good? Where's your inflection point? -2, F and -2, +2, F of +2. So remember, when they like to get those locations, what do they want to know? They want to know what? They want to know the y value. So you have to go back to the original function. So you go, okay, I'm going to plug in y here. 2 and 2, so that gives me 2 over, isn't 2 squared 4? And what's 4 plus 4? So this is really 1/4. Is that right? Oh, let me be careful. Wasn't that a square? So this is not true. This will be really what? That was x squared. So 2 squared is 4. And then 4/8 1/2. Yes. Yes. But notice something. It doesn't matter if that 2 is positive or negative, does it? Because when you square it, doesn't it make it positive? So they're both going to be what? 1/2. Do you guys know what I'm talking about? You're saying, what are you saying? What if you plug in a -2? What do you get? Isn't it also 1/4 or 1/2? Okay. So in other words, this will be 1/2. Okay. What do you guys think? Not too bad? Is that weird if I adopt the scary, whatever we call that? Scary something for the whole, the rest of the semester? I think I can see things better. In all honesty, I think I see things better if it's black. Maybe I'll get a picture of like a blackboard or something and try to write on the blackboard because I see it better than I do the white. I don't know why. Maybe the contrast. It's more contrasty. Do you guys see it or is it my imagination? What are you guys at home? You know, the bonbon crew. We got about 8 of you guys at home eating bonbons. You know, you guys are lucky. What are you guys doing? Casting spells. Works for you, Blanca? Does it look better? Does that look better, Blanca? You think? I might just adopt that. It's kind of, Halloween theme. Jeez, I don't know. Interesting. Yeah, I don't know about you guys. I can do this stuff. And I don't know, maybe like I said, if I were, when I was a kid, I'll tell you what I used to do or I would do tonight is I don't know, probably get a scary movie or something, sitting next to the bowl of candy and all the kids coming in. I'll be working on math while I did that. I used to remember, this is going to tell you my age. I used to remember specifically doing my chain rule derivative homework as the Dodgers were going through the previous, not the last World Series, but the one prior. That was in the 88 Dodgers. So that means I was taking Calculus 1 in fall of 88. Oh my God, Mr. Judge is such an old man. I was taking Calculus 1 in fall of 88. With Jaime Escalante. And if you didn't do your homework, he'd yell at you and he'd give you a pop quiz, show up and go, here you go, do this, derivative with chain rule. And you're like, oh. And everybody thought he held that pop quiz grade against you. He didn't. He would give it to you and he would grade it and he'd give it back to you. And if you knew how to do it, great, you were happy. If you didn't know how to do it, he graded it, you weren't. That was just his way of giving you feedback. But people were really mad because he gave you a pop quiz. Isn't that weird? But people would argue, it's not on the syllabus. You can't do that. And they'd complain and complain. Goes, I don't care, You say, hey, what do you guys think about that? Huh. His whole point was to give you feedback and to remind you, do your homework. You should be doing it now, not later. That was his way. And, it's interesting because I would say to you, he couldn't teach today. They would throw him out of the school. I mean, they tried to throw him out of the school back then. Yeah, they wanted to get rid of him. Even back then. He was too what? Radical. So they wanted to get rid of Jaime Escalante back then. Oh, everybody hated him. Other teachers hated him. Students hated him. Parents hated him. You know why the parents hated him? Because he made their kids do a lot of homework, and the parents were like, hey, that's too much homework back then. And he would say, I don't care. And everybody hated him. Could you imagine? So in order to change the world, what's the price you pay? You guys know? You face a lot of what? Hate. Dare change the world, you're going to face hate. Anyway, did we do this one already? I hope. All right, let's go back. Oh, yeah, I was so scared. I did my homework. I didn't want him to yell at me, so I was like, oh, I'm going to do it. I was that kid, they're like too scared. Hey. Please tell me I didn't. There we go. There it is. Yeah, okay. Where's that derivative? I think it's right here. Well, I'm going to use this version right here. Okay, you might say, why did I use that version? You know what I'm going to use? I'm going to use product rule. Because I need the second derivative, right? So this is the first derivative. Okay, you guys remember how to do the chain rule? I don't even know, I'm out of colors. Okay, here's, not chain rule. What are we using? Product rule. Do you guys notice that? Minus 2 cosine x. Derivative of what? Sine x plus 1. Now plus, do the sine x plus 1 here, right? Times the derivative of negative 2 cosine x. What's the derivative of sine? And what's the derivative of minus 2 cosine x? That's minus 2. Derivative of cosine, isn't that minus sine? So that's really 2 sine x. Is that right? Okay. All right. Second derivative. What do we have now? It's minus 2 cosine squared x plus here sin x plus 1 times what? 2 sine x. Okay, you guys okay with this? Now let me move some of this over. Maybe I can fit things in. I don't know. And then what do I say? You have to see, you're doing sign analysis on this, right? So for sign analysis, what do you think that means? You're going to do what? 0 equals all of this, right? Okay. What are you guys looking at again? What is this known as? This is I'm going to get my orange. A trig what? Equation. So I get to share with you guys again everything I've been sharing. If I go back, let's go back here. You guys already know, if you go to my trig portion here, 241. See this portion right in here? Trig equations. You guys take a look at that. There's a bunch of videos here for you guys. This one is under the algebra one. Okay? It's one of the algebra and using identities. So I'll give you again on your test the identity sheet, the same identity sheet. And you might say, where's that? It's weird. Oh, here we go. This sheet, you got some identities. I was actually proving identities earlier today in my trig class. I don't know, if you guys want to wake up a little early, you can see some of that too at that trig class. What do you guys think? I don't know. I've had students do it, not a lot, but okay. So let me show you guys how to solve this. All righty. You know what I see here? Here's what you're going to do. How you solve these equations is, notice, you have what? Sine. You got sine squared. Is that true? And then what do you have here? You got cosine squared. Okay? You replace cosine squared with 1 minus what? Sine squared. Okay? You guys okay with that? 0 is negative 2. 1 minus what? Sine squared plus 2 what? Sine squared. And then don't forget plus 2 sine x. And I keep saying I want to go back to my spooky colors. I'm going to. I got to look up that how do you be a cool Frankenstein? Man, I'm going to plan a whole year ahead. Anybody ever seen a Frankenstein costume where you go, wow? No? I I don't think I have. I don't think I have. Instead, it got to be a scarecrow. All right. Negative 2 plus 2 sine squared. Plus 2 sine squared. Plus 2 sine. Okay. Rearrange your terms, ladies and gentlemen. You're going to have 2, not 2, but what? Is that 4 sine squared? Plus 2 sine minus what? 2. Is that right? And then rearrange the terms. What's your terms? 4 sine x plus what? 2 sine minus 2 equals 0. You know what happens if you divide everything by 2? What happens? You get what? 2 sine squared plus sine x minus 1. Does anybody know how do you solve this? Because this should look interesting to you. What do you really have? You guys know? You're going to let this. You're going to let t be what? Sine. So that means you get 2t squared plus t minus 1 is 0. This is using what I call algebra to solve these trig equations, okay? Because this is what you have here. You're going to have to, what? Factor. So how do you factor? Negative 2, 1. Okay, this is product. Do you guys remember this here? Anybody remember the crisscross method? So give me two numbers multiplied together whose product is negative 2, but when added is positive 1. You guys can do this. What is it? The product has to be negative 2. The sum has to be what? 1. What are those numbers? Anybody know? Is it 2 and negative 1? Let's see. What's 2 times negative 1? Is that negative 2? Sure is. What is 2 plus negative 1? Is that positive 1? Yes, it is. So these are the numbers. Now be careful here. You guys remember the crisscross method? Because my daughter showed me this method. I didn't learn how to factor using the crisscross method. My daughter showed it to me. She says, Dad, use the crisscross method. I go, what are you talking about, crisscross? So here's the crisscross method, right? Typically, you would say this. You put t, you put t. Yes, it equals 0. The numbers you found here, you put over here. You put here. Okay? So you can say, is that plus 2? Is that minus 1? Yeah. But you're not done. You think you're done. If this leading coefficient, okay, was 1, you would be done. But it's not. So you say, what do I do with that? You divide by that number. That 2 goes here and here. Okay, this number here, this A term is 2 right here. So what happens with this now? What do you guys get? You get what? T plus 1. And this is, you go, is that, well, here's what you do. If you don't get a nice whole number, do you guys know what you do with this? Because 1/2 is not a whole number. Move the 2 here. It's 2t minus 1. It's a pretty nice method, ladies and gentlemen. I like the crisscross method. I really like the crisscross method. And in fact, I'm going to go make it whatever color that was. Okay, what do you do now with this? So solve for t. T is negative 1. And then this is going to be, if you solve for t, what do you get here? Right? Did you get t is 1/2? You solve that for t? What was t anyway? Okay, so what does that mean? Now remember, this is over what interval? They restricted the domain, didn't they? What do I mean by that? 0 less than or equal to x, less than or equal to what? 2 pi. Okay, so remember, that's actually a nice thing. Whenever they restrict the domain, I'm going to put a nice happy face, okay? Sorry. It's not a very good one. When is sine of this interval equal to -1? Do you guys remember? That's when x is what? Is that 3 pi over 2? 270 degrees? I think so. Do you guys remember the sine curve? That's all I do. You know how I know these? Sine curve. Graphing that sine. That happens at 3 pi over 2. What about sine of 1/2? That one, I have to go to my what? My right triangle, x, and this is going to be 1, 2. Do you guys remember what this angle is again? It's a special triangle. What angle is that? Is that 30 degrees? So that's pi over what? 6. But what do we remember? Let's bring it in. I'm going to bring it in. Oh, come on. Which one? I'm going to do this one here. I'll bring that one in. Yeah, whatever. I can't. Can I make it bigger? Right? All students take calculus. What does that mean? This is pi over 6. This is also what? Pi over 6. Okay, remember, all students take calculus means sine is positive in quadrant 1. It's positive also where? Quadrant what? 2. But in quadrant 2, this is pi minus that pi over 6. And don't forget, the arithmetic is 6 over 6. So you're going to get now what? 5 pi over 6. Okay, you guys okay with that? So this is doing sine analysis. So what comes next? Remember this? Just remember this here, okay? This is going to be from 0 to what? 2 pi. You have a restricted domain already. Is that right? This is your restricted domain. So we put pi over 6. We put 3 pi over 2. And then we put 5 pi over what? 6. Double check. Quadrant 1, quadrant 2, 3, and what? 4. And what is this here, right? 3 pi over 2, pi over 6, 5 pi over 6. Remember, this is all in the second derivative. And I would say to you, well, whatever would I say? Go back over here, I guess, whatever. Well, go back here. going to use this. T with sine, is that right? So this is the factored version. F double prime is sine x plus 1 times what? 2 sine x minus 1. Okay, what would you think some test points could be? What's less than 30 degrees? Right? You can say maybe a 15 degrees. What's between 30 and 230 and I think I messed up. It's not right. Right? This picture. These are the solutions here. Okay, this is 3 pi over 2, is that right? So pi over 6, 5 pi over 6, 3 pi over 2. So we're going to have to change this. The point is I need some test points. What's between 30 degrees and what? Oh, maybe 90 degrees. Okay. Need test points. What's between, what is that? 5 pi over 6, right? And 270 degrees. 180, I think? Use 180. And then what's more than 270? 300 degrees. Okay? So what I'm remarking here is you're going to need to test each one of these for the sine. And take a look. You're going to use this down here. You could use your calculator for that. Find what these are. Okay? Now, I think if we look at Desmos, just want to share with you guys. I think that was the function. Okay, 3 pi over 2. Got some concave up. Sorry. We're going to probably see something very interesting with this curve tomorrow. Yeah, we just got rid of all those nice points. Okay, so take a look at that because we're going to have to finish this one when? Tomorrow. This one's interesting. We got to plug in some numbers. What do you guys think? Anybody find an error in what we're looking for? No? All right. So, okay, ladies and gentlemen, we're going to finish this stuff, some of these up tomorrow. So, anyway, this will be on, But if you guys remember, this is where we left off. Is that right? And so here's what I would say I would do for these questions. Remember, we're investigating intervals of concavity. We want to find for a trig function where it's concave up, concave down, right? So we're going to go through all those little details. Now, what I'm going to do here for us is, since notice these angles that we have here, we have to check. Some of these angles, like 15 degrees, can't be done so easily, really by hand. It can be done. 15 degrees can be done. 90 degrees can be done by hand. 180 can be done. 300 can be done. So, but what I'm going to do, just to kind of share with you guys what you can do, right, is I'm going to go to my TI, but I got to make sure the mode in the TI is in degree mode. All right, so you got to be in degrees now. So make sure you're in degrees. And so I'm going to go back here, and I'm going to go down and say, oh, let's find it. Where is it? Is it in degrees? Yes, it is. It's in degrees. Okay? So we're in degrees because what do we have to do? We got to plug in 15 degrees. Is that right? And we have to plug in 15 degrees into that second derivative. So, this is what I'm saying. Sine is in the degree mode here. Okay, sine of 15 degrees. So let's see what this is. So let me try to put this all together here. Parentheses, we have what? Sine 15 degrees plus 1, close that, times parentheses 2 sine what? 15 degrees, close that, minus 1. And so what do you guys get here? Do you guys get a negative answer? Maybe we should scroll right in. I don't know if that helps us. Maybe that helps us a little bit more, see things. I don't really care about the value. We only care about the what? The sign. So that looks like quadrant 1 is, in fact, negative, ladies and gentlemen. You can see that there. Okay? You guys okay with that one? So now we get to go where? 90 degrees. You guys know what 90 degrees is for sine, by the way? Right? We're going to have to plug in the 90 degree. We're going to test region number 2. 90 degrees. 90 degrees. 90 degrees. So what's sine of 90 degrees? Isn't that 1? So this is 1, and this is 1. So I don't have to use my TI here for this, I think. 1 plus 1 is 2, is that right? And then this is 2 minus 1, which is 1. So region number 2 is, in fact, what? A positive region, ladies and gentlemen. Okay, so far so good. Here we go. 100 and what degrees? 80 degrees. What's sine of 180? That's 0. Right? So now what do you guys get? Right? Isn't this going to be 1? Isn't that right? 1 times what? 1 times negative 1. Is that right? 2 times 0. So that's a negative? Okay. So it looks like region 3 is, in fact, what? Negative. $300 degrees. 300 degrees. Okay, let's test that one. So we're going to plug in that 300. Okay, so this is where we're gonna use the TI here again, because even though we can do it manually, it's a lot harder. So anyway, whatever. So I'm gonna put here parentheses sine what? 300. Close that. Plus 1 times 2 what? Sine of what? 300. Close that. Minus 1. So double check that we're actually entering everything okay. Okay? And it has to be in degree mode. And what do you see here? That this here is what? Negative as well. Okay? So region 4 is negative, ladies and gentlemen. So, this is kind of what I would do to answering these questions here. Yes, you're using a little bit of technology. That's fine. And remember, this is the second derivative, so what are we finding here? This is concave what? Concave down, concave up, concave down, concave down, okay? So let's now communicate the answer, the conclusion, right? Your function is concave down on which intervals, okay? Remember, the domain was restricted from 0 to 2 pi. So, region 1, region 3, region 4. We have to describe those regions, 1, 3, and 4, okay? So here's how we do that. We're going to have to go from 0 to what? Pi over 6. Okay? And then how do we describe? That's region 1. We got to go from 5 pi over 6 to 3 pi over 2. So we're going to have to union 5 pi over 6 to 3 pi over 2. And this is both open-ended here, okay? Because at the endpoints, it's 0. That's not negative. And then finally, the last one would be union 3 pi over 2 all the way up to and including 2 pi, okay? So I want you guys to really take a look at this, that this is where it's going to have a, negative second derivative, and the domain was already restricted from 0 to 2 pi. So this is being concave down here. This is how we describe it. Now, what's concave up? F is concave up on what interval? You see this one here? This is region number what? 2. So what's that interval going to be? 5 over 6 to what? 5 pi over 6. Okay, so I want to make sure you guys understand. This is going to be where we have concave down, and this is where we have what? Concave up. Okay, pi over 6 to 5 pi over 6. Yes? Oh, very good question, because if I go back, I thought we have a question. Why do we include the 0 to 2 pi, right? Remember, this is our restricted domain. Okay? So this means here to include what? 0. This means to include the 2 pi, right? So when you go back at these endpoints here, you found where the function, the second derivative is what? 0. Second derivative is 0 for these values here. Okay? So when you test region 1, what do you notice? That includes what? 0 in region 1. Like the last region 4 includes 2 pi. So when we restricted the domain, it was really like from here, if I can find another, I don't know what color, pink. From here to here, that's your restricted domain. It included those endpoints. So that's why you need to include, when you go back down here, the 0, and you have to include the 2 pi with a square bracket. That's inclusive. All the others are open-ended because they're equal to 0 there, right? The second derivative is equal to 0 there. So here's what I'm saying. If you notice that endpoint, all these endpoints here have that open, they don't have a bracket, they have a parentheses. And that's because the derivative is 0, the second derivative is 0. And 0 is neutral. It's not positive, it's not negative. So you can't include it. And that's the little details where students make a mistake when they give the answer is right in there. Right in here. And you don't want them to, you don't want students to make a mistake on that. But it's all because of that nice restricted domain. Now, this question would be probably a lot harder unless there's a pattern if they didn't restrict the domain. If they don't restrict the domain, there's a lot more information there. And go back now to Desmos, right? You can say, so look at Desmos. What this is saying, it's concave up from 0 to what? To this value here. If I look at it, here's my 0, and then this value. Okay? This is where it's concave up. Pi over 6. Oops. Oh, we have some issue here. Anyway, I have to look. I'm gonna have to look this up. It's concave down from 0 to pi over 6. So well, let's look at Desmos. Okay, so pi over 6 looks like it's something like that, concave down. If we look, scroll in, yeah, it doesn't look like. I'd have to adjust the scalability. And then from this value, it looks like to that value, right? We are concave up. And then we have from this value all the way to this value here, and doesn't give it to us, we're concave down. Sorry, you can't see. So it kind of looks like it could be pretty good. But you know what I'm kind of curious about? Let's go back to Desmos. What if we take out that restricted domain? See this? It's periodic. So if we take out that restricted domain, you notice this function's periodic, right? The curve's periodic, that behavior, because there's sines and cosine curves. So it is periodic, but, you know, it's going to be interesting. How you write it would be a lot more work, those intervals. So I'm just saying that it's nice that they restricted our what domain. And, you know, so we include the endpoints there. So anyway. So let's go back here and let's find those worksheets we're looking at. And that's not in, you know, let's go to calculus. 1. See, this is whatever number that was. I don't remember what number. I could look into the sheet. Let's go back now. Let's try another one here, okay? Because we're looking at these intervals in concavity. I don't know how many examples you want to see there, but 4. Here's the function. Oh, I forgot. We didn't talk about this. Let's go back here. Any inflection points when you guys look at this? Where are the inflection points at? I see only, what do I see? Where are those inflection points? I think I see it where? Here and here. Is that right? Because those are the points where you change concavity. Anyway, so let's call that inflection. And what I'm not going to do, you know, it's a coordinate point. This is not interval. Pi over 6, I'll say to f of pi over 6. I won't go back and get it. What's the other one? 5 pi over 6? Okay, so here's your inflection points. Anyway. So, you know, now we have a more complete demonstration. And then I'm kind of wondering about something about this one here. This last one. I won't mention it. I'll just double check it on my own time. So I'll double check this one. Here's the function. 200 plus, what's this? 8x cubed? Is that plus x to the 4th? Okay. So do you guys remember that first derivative? It's probably in your notes, but if it isn't, we can do this pretty quick, right? We're pretty good so far. So far, so good? Second derivative. Isn't it 48x plus 12x squared? Okay, you guys double check that. Okay. Now, remember, you have to do what? Sign analysis. And it's on that first derivative. Second derivative. Let me put that right down on f double prime. Okay. Okay, so you really have 12x squared plus 48x is 0. Do you guys know, what do you do here with this? You're going to have to solve this quadratic. So how do you solve a quadratic? This goes back to beginning algebra, meaning divide both sides by, or factor out, you solve it by factoring. So you factor out the greatest common factor, and then you're left with the quotient here. Okay? So remember that. This is going to be the GCF, and this is your quotient. So 12x is 0. X plus 4 is 0. Divide both sides by 12. What do you get? X is 0. Subtract 4. What do you get? X is negative 4. Right? Aren't these... Now, these are your solutions. Remember, this is a polynomial function. All polynomials have the domain being what? All real numbers. So your domain here, all real numbers. That means every real number on the real number line. Now, that's, again, important for us. It's important because in sign analysis, what do? Right? You're going to have to now get out the what? The whole real number line. Negative 4. Let's go do this here. Negative 4, 0. What's that second derivative again? It's right here. Okay. And I like to use this form. Okay, so remember, you're setting this up. This is where the second derivative was 0. And you now have 3 regions here. 1, 2, and what? 3. So we need test points in each region. So maybe you test negative 5. I'll test negative 1. I'll test positive 1. And ladies and gentlemen, here you go. This is our second derivative. Okay. So what do we get here? You guys remember? We have to test this. Is that right? So we're going to plug in what? Negative 5. So what do we get here? This is negative 60. Negative 5 plus 4, isn't that negative 1? So what's the deal? That means a negative times a negative. So region 1 is what? Positive. What do we plug in now? It's negative 12 times, what's negative 1 plus 4? Isn't that 3? So a negative times a positive will give you a what? Negative. Now test positive 1 here. 12 times 5, which will give you what? It's positive. Okay. So, ladies and gentlemen, you're now ready for your conclusions here. And just colorize this a little bit. F is concave up on what intervals? Negative infinity up to -4 union 0 to what? Infinity. You guys okay with that one? Because that's where the second derivative is what? Positive. So let's kind of move it over. Maybe we can fit it in. Looks like we can. So there you go. It looks a lot better. Okay? So you're really describing regions, what again? 1 and 3. Is that right? Okay, you guys see what I'm saying? That's where the second derivative is positive. Interval notation. So now you also have F is what? Concave down between what? -4 and 0. So there's that answer. Easy breezy, lemon squeezy. You guys okay with that one? And then, what do we say here? Inflection points. Do you change concavity ever? Where do you guys change concavity? Here and where? Here. Happens for these values of x, -4 and 0. So you're going to have inflection points. And sometimes the book just puts, I'll write it out, inflection points. So there's 2. It happens where x is -4 and y, this is f of -4, 0, f of 0. Now this is a nice polynomial function. So you can go back to the curve and find the y value easily by just plugging in, 0, and then you get that 200. You'll get this value is 200. But the other one, you're probably going to have to use your calculator, okay? So I just want to say, you also have the inflection point question. They're going to want to know how to find those. So anyway, I'm just going to complete the picture. Concave up, concave down, concave up. This is the second derivative again. This is concavity. So there you go. I want to look at decimals, but I want to remember what this function is. 200 plus 8x cubed plus x to the 4th. Was that plus 8x cubed? Do you guys remember what the rest was? Was it minus x to the 4th? Plus, okay. Was it plus and plus, I guess? All right. Let me go back. Okay. We forgot the what? Extra 0. And notice this. I'm going to have to, with the y value, if I want to fix this. Well, what's the deal with the y value? Let's say positive 50. Maybe the x value would be 200 plus 8x cubed plus 4x. Yeah. So this is kind of a concave up situation. Okay. In this, look at this, opening this up. Anyway, not sure how to make that nice. And then you go up to 200 here. Something's wrong here. At 0 to the left, something's wrong with what we did. Let me go back. 200 plus 8x cubed plus x to the 4th here. second derivative now, right? So let me double check really quick. You guys find anything here? That's 24x squared. That's 12x squared. X is 0, x is 4. So what am I looking at? Concave up from 0 to negative 4, concave down negative 4 to 0. Concave down negative 4 to 0, concave up 0. Okay, that looks good. Concave up from 0 to what? Infinity. No, we look good. Sorry about that. We're fine. You know, hard to see. It looks like we're okay. It's just this. I might have to stretch this out on the x-axis. Right? Come on. Say negative 10. Positive 10. There we go. That looks a lot better. Okay. Looks a lot better. So concave up. Yeah. See this here? This point at negative 4. Oh, why is it not going? Oh, okay. No, somewhere over here. Negative 4. Sorry. We don't need that. So from negative 4 to 0, we're concave down. 0 to infinity, concave up. Concave up from negative infinity to 0. It looks good. So intervals and concavity, ladies and gentlemen. This looks very good. This is accurate. This is fine. All right. Okay, let's do another one. You guys want to do another one, or you want to move on? This is number, really, it's number what? Let's do number 5 here. Okay. If my function here, number 5, is x squared minus 1 to the 4th power, is that right? Oh, 3rd power. So I actually gave this to you guys before. So if you check your notes, didn't you get, 3 times x squared minus 1? This is squared times 2x. So, I mean, we can do it again here without checking our notes. This is 6x times what? Okay? So double check. I know you can't see. I'll make it so you guys can see. Double check. How do we get the double derivative now? What do you get? 6x ddx. Okay, so notice this. 2x squared minus 1, that'll be times 2x. Is that right? Because there's chain rule. You got to differentiate here. Okay, don't forget chain rule. X squared minus 1 to the 2nd power. Okay. So now we get what? 12x. It's more than 12x. It's going to be what? 6 times 4. Isn't that what? 24x squared. X squared minus 1. Okay. And that'll be plus 6. X squared minus 1 squared. Okay. Now what you can do, what can you do here? Right? Do you guys remember what I said you're going to need to do in our future? You got to look at that algebra for calculus students. What do you factor out? Looks like the only thing we can factor out for the constants is 6. We got to take out the greatest common factor. Now, it doesn't have an x term, but it does have a what? X squared minus 1. You always take the smallest power. Okay, smallest power. And now we need a what over here? We need a quotient over here. Okay. So what's the quotient? Do your division. It's going to be what? 4x squared plus x squared minus 1. Could you guys double check if that's okay? All right, double check here. All right, double check that this is our greatest common factor, and then this is going to be our quotient. Algebra, every calculus student should know. So I'm going to go back here to this derivative. So I have 6x, 2 times x squared minus 1 times 2x. Okay, 24x squared. And that's our second derivative. So what do you do with this again? Sign analysis, set that equal to 0. This is again, well, first of all, let me remind you guys, doesn't this become 5x squared minus 1? Set that equal to 0, the product here. So this is kind of why you have to factor this. So this implies you now have what? X squared minus 1 is 0, or x squared is 1. That means x is plus or minus square root of 1, or x will be what? Plus or minus 1. 2 solutions. And then what about this one here? This means what? 5x squared is 1. X squared is 1/5. So what does that mean about x here? X will be what? Plus or minus the square root of 1/5. Now remember, you have to do some rationalizing here. So x will be plus or minus 1 over the square root of 5. And rationalize the denominator. Okay, there you go. Okay, so, all right. Okay, so now remember, the domain is all real numbers because you're dealing with a polynomial. That's a factor with sign analysis. So we're going to do this will be all real numbers here. So what do we need? You guys know about these numbers? 1 over the square root of 5. Even if you went back over here to this number here. Isn't that smaller than, what's that smaller than? Isn't that smaller than 1? Okay. So the reason I say that is because you'll have -1, -1 over the square root of 5. I'll leave it like that. +1, positive square root of 5. And then I guess I'm going to have to move some things a little bit, okay? This is where that second derivative is what? 0. Region 1, region 2, 3, 4, and what? So now you have 5 regions here. 4 values gives you 5 regions. And you might even want to think about what that number is, because you say, what is 1 divided by that square root of 5? So here's second, square root of 5 here, right? And that number is 0.447. I'm going to use 0.5, okay? So I'm going to approximate that kind of crudely, okay? So here's what I'm saying. When you pick your test points now, give me a test point. You can say -2 is a test point, okay? And then you can say also +2 is a test point. You can test these here. But then the other test points now, right? How do we get this test point here? Oh, 0 is available. I like that. I always use 0 when it's available. So here's a test point. We use 0. But we're going to have to get these other test points now, right? How do we get these other test points? Give me a number between -1/2 and -1. Oh, that's kind of like -0.75. Is that pretty good, you guys think? -3/4? It's kind of like in the middle. And the other one would be a positive version of that, positive 0.75. Other test points. Okay, so this is all in the second derivative. So let's go back to that second derivative here. Okay, so what do you guys want to test? You want to plug in what? -2. So you might look in the book, and you know what the book does? It does like as a test point for some of these problems, it does ±2. Okay? Why do you guys think it does ±2? Because when you plug in that x squared, what's the deal? If it's +2, 2 squared is 4. -2 squared is also 4. So it tries to kill 2 birds with one stone. So you say, okay, that's 4 minus 1. Isn't that 3? And then 20 minus 1. Isn't that 19? So this is really strictly what? Positive here. Okay? And so this is strictly what? It's just killing 2 birds with one stone. And similarly, if I use that other value, I'm going to use the approximation, okay? Remember, this is about -0.5. And so I can say plus or what? Plus or minus again. Because again, if you square a negative, like you square a positive, the answer is positive. It just now means 1/2. What's 1/2 squared, by the way? Is that 1/4? So 1/4 minus 1, doesn't that give you what? That's -3/4, okay? And then here, 5/4 minus 1, well, that's going to be positive. Okay, you guys double check? 5/4 minus 4/4, that's positive. So a negative times a positive gives you a what? It's a negative. So this region here, I'm sorry, what did I do? I messed up. We want 3/4. Doesn't matter. It's going to still be negative. Sorry about that. I just want to be clear. Plus or minus 0.75. Plus or minus 0.75. Plus or minus 0.75. So 3/4 squared, isn't that 9/4? 9/4 minus 4/4, that's negative 5/4. 3/4 squared, 9/4, that's 20/4. 20 minus what? 16/4, that's a positive number, okay? Again, like I said, that means this region here of region 2 is negative, and region here, this is negative here, so you know, okay? Now we get to test 0. Plug in 0 as a test point. Here we go. 0, 0, 0. You get 6 times negative 1, and a negative times a negative is a positive. So, ladies and gentlemen, here we go. All right. Concave up. Concave up. Concave up. Concave up. Concave down now. Here. Here. And guess what's nice about this here? All of these points are what? They're all inflection points because you change concavity. You know, so this is kind of like a very interesting curve. You know, let's give the analysis, though. Let's answer the question. Then we could investigate the curve. Here's what you say. F is concave up on, let's see, region 1, 3, and 5. So 0 to negative 1, and then, well, we'll do it this way. Negative 1 over the square root of 5, positive 1 over the square root of 5, union 1 to infinity. S is concave down on what intervals? Negative 1 to that negative. So it would be negative 1 to negative 1 over the square root of 5. And then union, there's another one. One over the square root of 5 to 1. Okay, you're just describing the second derivative, positive and negative, and then you have all these inflection points, right? So I'll say inflection points. Negative 1, f of negative 1. Negative 1 over the square root of 5, f of negative 1 over the square root of 5. 0, f of 0. The last one. 1 over the square root of 5, f of 1 over the square root of 5. So how many inflection points do you have here? Negative 1, negative, oh, not even 0. Sorry, I apologize for the 0. 0 has no inflection point. So I'm missing the 1. Okay, you guys okay with that one? So let's look at, what's the curve? Let's look at what this curve looks like. X squared minus 1 cubed. So I'm going to look at this one here. Okay, and you go, based on what we did here, I think I have to adjust the y-axis. Not sure. No. I think the y, yeah, I'm sorry. Y-axis we're going to do from like -2 to 10 or something. There we go. There we go. Look at this. Isn't this kind of a, I can still, do a little better. And you can't see it, but remember this -1/2 point? You're changing concavity over somewhere right around here, right? So to the left of -1, it's concave up. To the right of -1, up to that -1/2, you have concave down. And then from -1/2 up to about here, +1/2 again, concave up, and I have to get that. And then from that, I don't know why it let me touch it. The -1, and then, I'm sorry, +1/2 to 1, concave down, and then from 1 to infinity, concave up. So you're looking at the concavity situation here. And that's very consistent with what we've disclosed here by doing the sign analysis on the second derivative here. This is our conclusion here. And again, we have the inflection points. We're changing direction, inflection there very often. Anyway, should we do the last one? Number 7. How about you? The function here is 3x to the 2/3 minus x. Is that right? Now, what's the domain? Do you guys know what the domain is here again? The domain is what? It's all real numbers here. Why is your domain all real numbers? This is something people overlook, because you remember, you do sign analysis, you need to know the whole real, you got to know the domain and restricted domain. There's no restriction on x, because even if x is negative or 0, you could take the cube root of negatives and it's a real number. You take the cube root of 0, it's a real number. So, ladies and gentlemen, it's all real numbers. Now, I don't remember what this derivative was in the notes, but I think it's 2x to the what? -1/3 minus 1. Is that true? Do you guys remember that? Do I have to look back? Intervals of increasing, decreasing. Yeah. There it is. Okay. Here's what I'm going to do. I'm going to keep it like that. You guys okay with that? You say, why would I keep it like that? Because I think this second derivative will be a lot easier. -2/3 x to the -4/3. Is that true? Do you guys need to see all the notation still? Maybe? You say, are you differentiating that prior derivative of 2x to the -1/3 minus 1? And you say, is that second derivative going to be by properties 2 dx x to the -3 minus what? ddx of 1. And what's that going to be? 0. 2 -1/3 x to the minus negative, isn't that -4/3? So we get -2/3 x to the -4/3. Okay, and that's going to be a negative 2 over 3x to the positive 4/3. So do you guys remember when I shared with you how to simplify this here? How do you simplify that? Isn't that x cubed root of x? Or that second derivative is negative what? 2, 3x cubed root of x? Double check, ladies and gentlemen, I have that correct, because for sign analysis, you guys know what that means? You set the denominator equal to 0. And that means x to the cube root of x is 0, which means x is 0 or the cube root of x is 0. This means x is 0. The point is, this is undefined. The second derivative is undefined at 0. All right, you guys okay with that? That doesn't mean, don't think, oh, what does that mean? It just means the second derivative is undefined. This is not the first derivative. Okay? So 0 is important. You are undefined here. Region 1, region 2. This is on the second derivative. So it's kind of easy for the test points. Negative 1, positive 1. I like these values. Okay, because you're going to work with this second derivative here. And in fact, you could go back over here, if you like. So what happens when you put a positive 1 there? Right? You guys know, what is 1 to the 4/3? You know what that is? That's 1. So what I have negative 2/3 times 1 means region 2 is what? This is negative. Don't forget, you have a what here? Negative constant. Now plug in negative 1. Negative 1 to the 4/3. What's that going to be? Is that positive 1? Think so. Think so. So similarly, what happens? You have what? Concave down. Concave down. Finish the analysis. F is concave down on what intervals? Negative infinity up to 0, union 0 to infinity. This is where it's concave down. Okay, it's everywhere except what? 0. Does it have any inflection points? No, you don't change concavity. Does it have any region that's concave up? No. So you might even say this, F is what? Not concave up. F has no inflection points. Okay? And that's the analysis for this curve here. At least the analysis in terms of concavity here. So even in Desmos, that curve, the original curve here we have is what? 3x to the 2/3 minus x, right? So let's see if this picture is worth 1,000 words. There we go. And I think I'm going to have to switch because you can't even see much. Oh, there we go. There we go. So here's my point to you guys. To the left of 0, this curve is concave down, does not hold water. To the right of 0, the curve does not hold water, concave down. Would you guys agree with that? You guys think, is that pretty good? Okay, so I kind of want to mention that to you guys here. And then I'm kind of looking at this last thing here. I'm looking at Desmos. We have this curve here. Y equals X plus what? Cosine X. And I'm going to restrict the domain here. Because that's in general. You go, oh my gosh, that looks kind of interesting. Okay. So what do we do with this one? Where's my notation? So if I restrict that domain, like in question number 8 here, okay? See at the bottom, number 8. We can talk about increasing, decreasing, blah, 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 blah. Is that right? So here's what I'm going to do here. What time do we have here? I don't know. Do we have time for this one? Or how about this? I'm going to do this here. Let's go to the assignment portion here. Okay. Where is this sheet? Say, Mr. Judge, you ever give extra credit? Hardly ever. But I'm going to say what? I'm going to say determine the following for question 8 on the worksheet here. And even put a link. Okay, you're going to say what? 1. Intervals of what? Increasing / decreasing. Okay. 2. Relative max or relative what? Oh my gosh. Relative min. What happened? Three. Intervals of concavity. Is that right? For possible what? Inflection points. So what I'm essentially saying to people for extra credit, I don't know how many points. 10 points, 15 points, 10 points. Let's say 12 points. Assignment group. I don't think they can display it as points. Yeah. Mission type. Right. PDF. When should we make this due? What's available from today? What's today? November 1st. At what time is it? 11:30? Okay. Ah, come on. a.m. When should we make this due? What do you guys think? What's today? Today's the 1st? Let's make it at Friday at what time? Friday at noon? Midnight? 12 p.m. Friday. Come on, what happened there? Friday at... Okay. That's weird. That's what it is, this date here. This date has to be 12. Oh, that's what it is. So as you guys can see, I'm going to let you guys finish that last example. It's not too bad. It's a trig example, actually. It's probably nicer than the other one we did. Because it's really finding, if I look at that derivative, I won't give you a hint. I could read the derivative off, and then no, I set that equal to 0, and you get some nice things. This one's not too hard to do. This would be a good, like, even test question, in all honesty, because that one's not that hard. So give it you guys an extra credit. You might want to enjoy that. Find those things, because those are the kind of questions that they ask you on your next test, okay? Anyway, we're going to let you guys go.